Good morning, kids. Today's class we are going to discuss the KTG and the thermodynamics. KTG and the thermodynamics in one shot. A good revision of concepts and formulas is what I'm going to explain in this particular video class. So, what is the basic thing like? So, how to utilize this one shot? You have to watch the video first. Then learn it, not only mere watching. So this may be 1.5 or 2 hours video. Learn it. Very beautiful, important concepts I'll be explaining. Learn them. Means learn in sense, show like a put effort, try to understand why only like this, all everything, no. Grab those ideas, important ideas. Then afterwards, remember them. Not only learning, you should remember it. Remember it. All the formulas are there. Make a list of them. Write it down, note it down, and daily revise them. Recollect them. Then next again, solve the PYQ. Only JEE Main. Those who are preparing for JEE Mains, solve one or now time is less, I think. Those who are dropper, solve 5 years. Those who are preparing for only April, at least solve few. For every this particular video lecture, no, you solve around 20-30 questions. You get some basic picture. Okay, how you can use all this what all you learned. Learning, remembering, solving PYQ. This is a very fundamental preparation for JEE Mains. As you solve PYQ, you'll get an idea how to use all this knowledge. Okay, then afterwards, those who are preparing for JEE Advanced, learned, watch, learn it, make a list of all the formulas, daily revise it, and solve different types of numerical. Or in video lecture, I explained KTG Thermodynamics, more than around 140 questions are there, advanced level. Watch them and learn it. The time will be less, so into 1.5 speed you keep it and grab the ideas involved in those problems. Like that also you can prepare for JEE Advanced. There's overall the method you should follow here. I'll put it this one. Learn means here ideas, concepts which are there, you have to understand. Then all formulas you have to revise. Then solve PYQ. Solving problems. These are fundamental things. Next question comes like how we should plan for this KTG and thermodynamics. Can theory of gases and thermodynamics in one shot. We are actually discussing this in the now this is the can theory of gases and thermodynamics in one shot. The methodology first, the postulates of KTG, very important concepts, will be assuming them and will move forward. That's the postulates of KTG. Some good conceptual questions they'll ask you here in KTG also. Then what do you mean by ideal gas, real gas? A small basic idea which will help you. Lot of good conceptual questions they'll ask you here. That's why we'll have small discussion on this. Then we'll explore the pressure. What do you mean by pressure? Already you know some basic concepts about the pressure in a fluid. The same thing for gas, and we'll give some examples by that pressure and what are the basic uses of it. Then we'll discuss the RMS speed of gas molecule, then degree of freedom concept, intensity of gas, mixture of gases, then rate of collisions per unit area, then pressure based problems. This is about all the KTG concepts. Then we'll enter into first law of thermodynamics. This is about the conservation of energy principle. Then all the basic process, isothermal, adiabatic, isobaric, isochoric process. These things we'll discuss, and graphical conversions also. Then polytropic process. Then we'll discuss the work done by gas problems, Carnot heat engine. Then efficiency of gas in full cycle. We'll be discussing those things here. Some problems, I'll give some idea. These things we'll be discussing it. Any number. So these are the And Carnot heat engine, second law of thermodynamics. The refrigerator also will come in the heat engine, which is not there for JEE Mains. Carnot heat engine also not there for JEE Mains, but efficiency concept is there. This is all about the planning is what you should do for JEE Mains as well as advanced. Okay, kids, now. So let me revise this one. Let me give the very good revision of this KTG and thermodynamics. Really, you are going to enjoy. Very good ideas, diagram-based explanations I'm trying to give you. We'll start with the postulates of KTG of gases. So these are all red color one, orange color one, what you can see gas molecule, they are moving randomly. How do this given molecule, it will be moving randomly. This will go collide. Why do the zigzag path like this? They will be colliding. This random motion is due to collision between the adjacent molecules between the walls of the container. So all gas are made up of molecules that are constantly and persistently moving in random direction. How the molecules, they'll be moving in random direction and they'll be moving at a different speed. The separation between the molecules is much greater than size of molecule. So here you can see here, there's a separation, there's a radius. If you take two molecules, there's a separation, this will be radius. R will be very much less than X. And there's one basic idea which will help us a lot in defining some concepts, fundamental concepts in defining. So there's a molecule. These are the two molecules. The radius is R, the separation. Here R, the size of molecule will be very much less than the distance between molecules. So what is the use of this one? Suppose you calculate the moment of inertia. The moment of inertia here about this axis. Let me separation, let me call L. Moment of inertia about x-axis will be 0 because the size of molecule negligible. Then moment of inertia about y-axis will become mass of the molecules Bm will be 2m L by 2 whole square. Concepts it will be. So the separation between the molecules is much greater than size of the molecules here. When a gas sample is kept in container, the molecules of the sample do not exert any force on the walls of the container during collision. Okay, fine. Then means there won't be attractive force between them. The molecules will not exert any attractive force between the with the wall of the container. The time interval of collision between two molecules and between molecule and the wall is considered to be very small. The collision time will be negligible. So what's the meaning of this? Collision time is negligible. All the collision between molecules and even between molecules and the wall are considered to be elastic. They'll enter collision. There won't be any, there'll be exchange of velocities will occur everything, but there won't be loss of energy. All the collisions are said to be elastic. They'll collide elastically. All the molecules and gas obey the laws of motion. So what all we have discussed, the change in momentum, everything, the laws of motion is to be obeyed. If a gas sample is left for sufficient time, it eventually comes to a steady state. The density of molecules and distribution of molecules are independent of portion distance of time. Means what is the behavior of gas in this region? The same behavior the gas will behave here. Means either you measure pressure here or here will be same. You measure the temperature here or here will be same. You measure the kinetic energy here or here will be same. Means like I say the pressure of gas. We should not ask like sir which part. Everywhere the pressure of the gas will be same. That's the meaning of steady state. Very very important idea. Okay sir, how do the gas will collide? How do they move? Now there's a vessel, there's a glass vessel. So there's some vessel container. Here we'll introduce the n moles of ideal gas. So these molecules, they'll be going and colliding. Like this I can introduce n number of molecules. Now you can see these molecules, they'll collide between adjacent molecules and they'll be colliding with the wall. What is the wall? There's a wall. This particular thing is a wall. There's a wall, there's some vessel. cubical vessel. Inside this blue color one, they are molecules and they are moving randomly in all direction. Why do this random motion? Because of collision between the molecules and between the collision between the molecule and the wall, because that is responsible for random motion, and different molecules will be moving with a different speed, and there's no force of attraction. You can see size of molecule will be very small compared to distance between molecules, and no force of attraction between molecules and the wall. This is what basically a given molecule, if you see this, is a very random, how it will move, we can't predict. Very random motion will be taking place. This is what happens with the gas molecule. Whenever n moles of gas come, you should have this imagination. This imagination is what you should generate. You should have this basic picture. So what is the thing? The molecules will be colliding with each other, with adjacent molecules, and will be colliding with the walls. You can see on this wall, the molecules come and collide. You can see it also. The molecules will collide at the bottom also, side wall, bottom also colliding. On the side wall also the molecules will collide. They'll collide with all the surfaces in which it comes in contact. This is a basic imagination students should have before entering the KTG or thermodynamics. You really enjoy it. You're going to enjoy it a lot. Fine. Okay, kids, you had some small basic discussion. So this molecule will collide. Why do this random path? Because of collision with adjacent molecules between the walls. And the size of molecule very small compared to distance between molecules. All collisions are elastic. No force of interaction between molecules and between molecule and the wall. These are all the postulates. And steady state, what you measure the pressure, volume, temperature, what you measure pressure, temperature, it will be same everywhere. That's the meaning of steady state. Like this is what the conclusions. The next one, the space volume to molecules ratio is negligible. Means the volume occupied by the molecules will be very less compared to volume of the container. The space volume to molecule ratio is negligible. Means we'll calculate the volume of each molecule. I'll multiply the number of molecules. You compare with the volume of the vessel, it will be lesser. The space volume to molecules ratio is negligible. Very fundamental thing, very, very useful for us. Because of this, the gas will possess compressibility. Because of this parameter only, the gas we can compress it. There is no force of attraction between molecules at normal temperature and pressure. The force of attraction between molecules builds when the temperature decreases, pressure increases. We are going to discuss at normal pressure, temperature. So definitely no interaction potential. No interaction potential. Like in gravitation, G M1 M2R, like that we should not consider anything here. Or in the electrostatic interaction KQ1 Q2R, all those things you are not supposed to discuss here. Don't consider them. There's a meaning of the ninth one. There's a large space between the molecules resulting in continuous motion. Yes, you can see this space here, this one, all this space. There's a large space, they'll call it. The free movement of molecules result in collision, which is perfectly elastic. So how the molecules will be moving in zigzag path. Why do they zigzag path? Because of collisions. The molecules have kinetic energy due to random movement, but the average kinetic energy of these molecules differs with temperature. That we'll discuss in the KTG derivation. Molecules exert pressure on the walls of container. These molecules will go and collide, and because of collision, force will act, change in momentum of molecule. Because of that force, the force by area will become pressure. Of all very important, the molecules collide with each other, no energy is gained or lost. All collisions are elastic. The space occupied by the molecules of gas in container is very negligible compared to volume of the vessel. These molecules always have linear motion. We'll just assume straight line like this. They don't move in curved path like this. So zigzag path. Okay, there's a meaning of straight line. And these are the postulates of KTG. Based on this is what all our derivations. Theoretically, why this is very important? You must know all these things. Any conceptual question, if they ask you, you can deal those conceptual questions with the help of these postulates. Okay. Next, what do you mean by real gas and ideal gas? In real gas, the particles will have a volume. The volume of the molecules should be considered. In case of ideal gas, the volume of the particles will be negligible compared to volume of the vessel. Energy is lost in collision. They'll encounter in inelastic collision the real gas. Right? Here will be the ideal gas. Collisions are elastic. Then there'll be force of interaction between the molecules. Between the molecule and the wall also. Here the force of interaction negligible. Then how, but sir, where is ideal gas? The real gas only we have to make ideal gas. So for that what we should do, like a normal temperature and low pressure. The real gas will behave like an ideal gas. This is a basic condition. Next we'll discuss the, now the molecules will be moving. These molecules, when they're moving, they'll go and collide. No, the molecule will go and collide. Due to collision, there'll be change in speed. So here we'll deal with this one. The momentum, change in momentum, delta P. This should be equal to force by area. Why do this change in momentum is there? I'll come for this. When the molecule goes and collides, its momentum will change. So here we can write it theta 1, theta 2. Let's assume that one. What is the change in momentum? mv2 cos theta 2 minus mv1 cos theta 1. Hope you remember this. This will be the change in momentum, and this will be minus of minus. Since all collisions are elastic, v1 equal to v2, theta 1 equal to theta 2. So this will become how much? 2mv cos theta. I need to take some time, no, to collide. So because of this change in momentum per unit time, we'll get the force. This force per unit area will become pressure. So this molecule, when it collides, it will exert force. That force per unit area will become pressure. Like that, millions of molecules colliding. This molecule will collide. This molecule will collide. This molecule will collide at a given instant. So each molecule will exert force F1, F2, F3, F4, F5. The resultant force per unit area will become pressure. Like that, the molecules will be colliding with the piston, will be colliding with the side wall, will be colliding with the wall, with the side bottom, with the side wall. So like that, this force per unit area will become pressure of a gas. What is V? V is the volume of gas. P is the pressure. T is the temperature. Like this, we are going to introduce the parameters of a gas here. So this is ideal gas. And what are these? These are molecules. Okay, fine. Now you can see this. The molecules here will balance the weight of this piston. Next, there is a piston. Who will balance the weight of piston? The molecules only. One molecule? No. Millions of molecules, when they come and collide, they'll balance this. Okay, fine. Now I'll add some load on the piston. Then weight of the piston and weight of the block. Then here who will balance this? The molecules which are going and collide. So they'll go and collide here like this. They'll exert a force. The net force is what? Pressure force. P2A. Here the net force will be P1A. Here P1A will balance M1G. Here P2A will balance M2 plus M1G. The molecules are only balancing the weight of piston. I'll give one very beautiful statement. Resultant force exerted by molecules on the piston will balance weight of the piston. That's why the piston is at rest. There's a central part of our KTG and thermodynamics. That's why I'm spending more time. Okay, so like a what? Now this person is standing. Now who will balance the weight of the person? The pressure force. From where this pressure force, when millions of molecules, when they go and collide, they'll exert force. The resultant force will balance mg. So Pa minus mg equals 0. This is the beauty of KTG. Trying to understand this one. If one more person comes, then more number of collisions will occur. If one more person stands, more number of collisions. More number of collisions, more force. Then more force means more pressure. Like that, the idea of the pressures will come here. That's the basic idea. So when you add load, more number of collisions will take place here. If you see the previous one, when we add load, number of collisions will increase here. Here, why means because the more weight has to be balanced, more pressure force. More pressure means more force. The more number of molecules should collide, more collisions will occur. Agreed? Yeah. Next we have to derive an expression for RMS speed of a gas molecule. So we'll consider the volume of the material, volume of the vessel, let it be V, where V is equal to LQ. It contains n mole of ideal gas, and the molecules will be moving randomly. Here, the time taken by the molecule to move between successive walls for successive collision, that will be 2L by U1. Here, this length 12 by, it will move like this and again returns back now. So what is the time it will take here? L and L, and it is moving with a speed U1. So what is the total time will be? L by U1, L by U1. So time will be L by U1. So the number of collisions per second on phase A. How many collisions per second here? 1 by T. This will be the rate of change of momentum. We'll define this one. M1 U1 square by L equal to force on A due to one molecule here. The area of one phase will be L square. The n number of molecules are moving in x direction. So the total pressure on phase A will be this much. Similarly, average pressure, like that, there will be n number of molecules will be there. So the average pressure will be 1 by 3 will be this one, because at any instant of time, 1/3 of molecules will be moving along one x direction. So 1 by 3 will come. If we write this, nc square equal to this one, where c is the mean square velocity, pressure equal to 1 by 3 into m L cube n c square. But here L cube is the volume. If you solve this, we'll end up this equation. PV equal to 1 by 3 n m c square, where c is the velocity of the particle, or say what you can call like a RMS speed of the molecule. So this will be something very important equation we have brought it. Now total mass of the gas is m, density of the gas will be mv square. So here m volume mn by v. So if you solve it, we'll get P equal to 1 by 3 rho c square, where c is the RMS speed of the molecule. Like this, we'll define it. In books, we have equation like this: Nm Vrms square, where this will be P equal to rho. So or RMS speed equal to 3P by rho. Okay, calculate this. So this is called like a root mean square speed. Root mean square velocity of the gas, where P is the pressure of the gas here. What is the RMS speed of the gas molecule? It's not something like you can see like a 18,300 at STP, a standard temperature pressure, means at like a 27 degrees Celsius and at 1 atmospheric pressure. Well, what is the speed of this? 1,800, like a 390 9 meter per second. They'll not be moving with a small speed, a very high speed it is. With this much of speed, the molecules will be moving inside the vessel, and they too they'll be moving in random direction. So here we will express this RMS speed. RMS already we have derived this PV equal to 1 by 3 Nm VRMS square. Here the terms will be using mass of molecule, small m mass of molecule, molecular mass m naught, capital M mass of gas, small n number of moles. Capital N is number of molecules, small n number of moles, Avogadro number, Boltzmann constant, universal gas constant. And this ideal gas equation PV equal to nRT. P is pressure, will be Newton per meter square, SI unit, volume, cubic meter, number of moles, this will be mole, universal gas constant, temperature in Kelvin. And these are some relation between the quantities. Now from this ideal gas equation, I'll substitute this one here. This will become nRT VRMS square. So this nRT, so here what is n? N we can write it as m into n into small m. This will become mass of gas. Number of moles, what we can write it as mass by molecular mass. So therefore VRMS equal to 3RT by m naught. Okay, fine. This further, the same equation PV is equal to 1 by 3. This n into m will become mass of gas. 3P. Mass by volume. Mass by volume will become density. So where VRMS equal to 3P by rho. What is R? R equal to KNA. So I'll substitute this further. VRMS equal to 3. R will be KNA T by molecular mass. We can write M into Na. Na get cancelled. So this will become 3 KT by small m. Like this, we'll express this for number of moles. The same equation for number of molecules will be nkt. The same ideal gas equation PV equal to nkt. PV equal to nRT. The ideal gas equation. Number of molecules, Boltzmann constant. Number of molecules, universal gas constant. Like this, the molecules will possess average speed. Average speed will be 8 by pi RT by m naught. 8 KT by pi m. 8 P by pi rho. Whatever the most probable speed is given by 2 RT by m naught. 2 KT by small m. 2P by rho. The most of the molecules, the speed within most of the molecules will be, and this is average speed. All these formulas you are supposed to remember. There's a very important thing which I'm putting in one screen itself. You can take screenshot. It will going to help you a lot. Okay, sir. Then what is RMS speed? Why you are calling RMS speed? So let's have a small basic discussion on it. Then we'll move on to the other concepts. Inside the vessel, we know inside the vessel, what is the state of molecules? The different molecules will be what is the state of this molecule? The different molecules will be moving with the speed V1, V2, V3, V4. You can see that different molecules, they are having the different speed and they are moving in different directions. Then I will what is RMS speed? We have derived, sir, what is RMS speed? the total energy of the gas. There are n number of molecules are there. Mass of each molecule is m. Then what is the total kinetic energy of the gas? That should be equal to sum of all molecules. They're having same mass because they're identical, we assumed. So I think we'll write it like this. Like this, so on, m Vn square by 2. Then what is the kinetic energy of this? The sum of total kinetic energy of each molecule. Then this, what is the kinetic energy? Shall we write mass of gas? Total mass of gas. Then one speed will come here, that I'll call Vrms. This will become m by 2, V1 square, V2 square, V3 square, Vn square. What is the mass of gas? We'll write n. Mass of total mass of gas should be equal to number of molecules into mass of each molecule. Okay, fine, like this. So this m and m will get eliminated, 2 will get eliminated. Vrms square equal to V1 square, V2 square plus V3 square, so n Vn square by n. This will be the RMS speed. So what is RMS speed? It will indicate about the energy of the gas. No? It will give you about the information about the energy of gas. That's why, so further, everything will be under root of this quantity. Okay, that's why it is called as a root mean square. Okay, fine. So this is one basic information. Next, we'll take the Maxwell speed distribution curve. If you look at the speed distribution curve, Maxwell speed distribution function. So what is this Fe? Fe will be number of dN by dV, we'll call it. The fraction of molecules which will having a speed dV. So this is also nothing but, we'll write it as dN by dV. Means the dN molecules will be having the speed around dV. This I'll plot it as a function of speed. This will be the equation. Then here we'll bring the most probable speed, average speed and RMS speed. So inside the vessel there are some molecules which will be moving with a high speed and their number will be lesser. There are some molecules which will be moving with a very less speed and their number will be less. Then most of the molecules, they're moving with one common speed, that's called a most probable speed. Like this means inside the vessel we'll have some molecules which will have speed more than Vrms. We'll have some molecules which will have speed less than Vrms. We have some molecules which is going to move with a speed equal to RMS. Then what is a Maxwell-Boltzmann distribution curve? It describes the distribution of ideal gas particles at different temperature in a given state. Moreover, the distribution is further used to calculate the energy of activation and temperature ranges required for chemical reaction. Actually, the Maxwell distribution curve, which will help us to predict whether the chemical reaction will take place or not, at what particular energy the reaction will take place or not. That's actually the purpose. We are going to use this more in the chemistry, less in physics. This idea is very important. Use it. At what temperature the chemical reaction will take place for that purpose. So as we increase the temperature, then definitely the RMS speed will increase. So most probable speed will increase. So the curve open will have the less, will be, you can say the peak will decrease here and more energy will be present inside this. Here area under the curve will give total number of molecules in a vessel. This is the basic idea of the Maxwell-Boltzmann distribution curve. Next topic will be having the degree of freedom. The monoatomic gas, the one particle. It can move along x, y, z. So what do you mean with degree of freedom? Number of independent ways in which system can possess energy. For monoatomic gas, it can move along x, y, z. So the velocity along x is independent of velocity along y independent of velocity along z. So all these kinetic energies along x, y, z, they are independent. Of course, Vx equal to Vy equal to Vz, but they are independent. So number of degrees of freedom will be 3. Why Vx equal to Vy, Vz? According to Maxwell's law of equipartition of energy, what all energy if you give it, that will be divided equally among each degree of freedom. If you give 9 joules, 3 joules along x, 3 joules along y, 3 joules along z. Like that it will be splitted up. This is one basic property of the molecules. So how many degrees of freedom monoatomic gas will be 3. Then diatomic gas molecule. Size of molecule will be very much less than compared to the distance between the molecules. So therefore R will be very much less than R. Then because of that, moment of inertia about x-axis will be 0. There's a basic reason. Okay, agree with this. Now the molecule can move along x, along y, along z. So 3 translation. It will be rotating about x, y, and z axis. Then moment of inertia about x-axis will be 0. So how many ways it can possess energy? By moving along x, y, z, 3 translation. Then by rotating along y, z, about x-axis also will rotate, but the energy will be only contributed by rotational motion about y and z. So 3 rotational. This will become negligible. This will be tends to 0. So how much of energy? 3 translational, 2 rotational. So the total rotational energy will be given by this one. Then according to Maxwell's, if T is the temperature, then in each degree of freedom, how many are there? 3 degrees of freedom. In each degree of freedom, half kT will be present. Half kT. Why half kT? Because if you see the average translational kinetic energy, the total kinetic energy of the molecule is given by 3 by 2 kT. Sir, how you can write directly these things? Sir? We know VRMS is equal to 3 kT by m. Then m VRMS square equal to 3 kT. Then m VRMS square by 2 equal to 3 kT by 2. The total kinetic energy of this gas molecule, which is having RMS speed, equal to how much? 3 kT by 2. According to Maxwell's, each degree of freedom, half kT. So total kinetic energy how much? 3 by 2 kT. Similarly here, kT by 2 due to translation, kT by, here due to rotation will not be there. Here kT by 2 due to translation, kT by 2 due to rotation, kT by 2 due to rotation, kT by 2 due to translation. So the total energy, this will become 3 by 2 kT, this will become kT, half kT, 0 it will be, kT by 2 will be kT. So what is the average kinetic energy of the diatomic gas will be 3 by 2 kT plus kT will be 5 by 2 kT. Average translational kinetic energy of all molecules will be same, either monoatomic or diatomic. Average translation, average kinetic energy will be different. The number of degrees of freedom will be 3 due to translation, 2 due to rotational. Then at higher temperature will add up degrees of freedom due to translational, rotational and vibrational. 3 plus 2 due to vibration. So this will be like a spring system, you can connect it here. So due to spring, it will have the elastic potential and about center of mass, it will be oscillating up. So 2 more degrees of freedom you can add up. This is at higher temperature. At normal temperature, it will have 5 degrees of freedom. Diatomic gas. Then linear polyatomic gas. Again, the size of molecule will be less than L. Then the molecule will be moving along X, along Y, Z, along Z, all 3 different axes. So 3 translative motion. Then the moment of inertia about x-axis will be 0 because of R very much less than L. About y-axis, z-axis will be non-zero. That I shown it. So this translation, this will be 0. Why? Moment of inertia will be 0. The total will be only due to, we'll write IY something. The total moment of inertia will be only due to the rotation motion about y and z axis, or the total rotational kinetic energy. So the total energy will be due to translational 3, rotational 2, the total degree of freedom will be 5 1. At higher temperature, you add 2 more vibrations. Linear or diatomic will be same. Non-linear polyatomic gas. Now the molecule can move along x, y, z. It can rotate about x, y, z, and moment of inertia about x-axis will be non-zero because R, L very much greater than R. Moment of inertia about all 3 axes will be non-zero, whereas this will be now non-zero. So 3 translational, 3 rotational. Total will be 6. At higher temperature, 2 more you have to add up due to vibrations. This will be due to vibrations. Will be 8. There's a condition which you have to remember. There's a vessel. There are n number of n moles in there. There's having a temperature T. Then the total energy of the gas. Intensity, the symbol will be using U. The total energy of the gas is nothing but sum of kinetic energy of all molecules. It depends on what all. The total energy, it depends, is directly proportional to number of moles. As you increase the more number of molecules, then the kinetic energy of the total kinetic energy of the gas will increase. The total kinetic energy of gas is nothing but called as intensity of gas. Total kinetic energy of a gas. That only will call internal energy. Then, as number of molecules will increase, then the kinetic energy of the gas will increase. So therefore, the intensity is directly proportional to amount of gas. Then it's directly proportional to temperature. As you increase temperature, RMS speed of molecule will increase. Then definitely kinetic energy of each molecule will increase. Total kinetic energy of the gas will also increase. Then it also depends on degree of freedom, because monoatomic gas, how much of energy it will have. Average energy of the monoatomic gas 3/2 kT. Average kinetic energy of the diatomic gas 5/2 kT. So even the degree of freedom also depends. So using all this, we'll write like this: NFRT/2, where F is called as degree of freedom. This we'll write it as CV, FR/2. So this will become NCVT, where CV is called as molar specific heat at constant volume. Then CV we can also write R gamma minus 1. Then further, Mayer's equation Cp minus Cv equal to R. Then intensity we can also write Nr gamma minus 1 T. And delta U should be equal to NCV delta T. Change in intensity directly proportional to change in temperature, where gamma is called as Cp/Cv. Now what is Cv? Cv is molar specific heat at constant pressure. What is gamma? Adiabatic exponent of a gas. And these are all formulas you have to remember. Intensity depends, intensity is directly proportional to temperature. This is what for a given gas. For a given gas, okay, this one. Next we'll discuss the mixture of gases. This will be one more important idea which we'll be using here. So let's assume that it contains the hydrogen, also like a helium, and nitrogen, anything. There's a diatomic gas molecule, there's a monatomic, and they'll be moving randomly in all directions, they'll be colliding everything. Then what is the all the quantities? I want to calculate the total energy of this gas. So how come they'll be moving? The mixture of gases, how they'll be moving? There's a vessel. In that first, I will send the some set of gases. These are some molecules. These are some say monatomic gas molecule. Then I will send the diatomic gas molecule. Now you can see that both will be moving randomly, both will be colliding with each other, both will collide with the walls of container, and both will present throughout the volume of the vessel. This is what happens with the mixture of gases. Getting some idea? Both will be colliding, both will be moving randomly. This will become mixture of gases. So now what is the total kinetic energy of gas? Sum of kinetic energy of all the molecules, both monatomic as well as the diametric. This is some general idea is what you should imagine now. Mixture of gases will be of like this. Got the idea no? Now the total energy of the gas will be, the total energy will be energy due to individual gases. So first we'll calculate the effective CV of a mixture. N1 CV1 N2 CV2 by N1 plus N2. Then same thing, effective degree of freedom N1 F1 N2 F2 by N1 plus N2. Then gamma of a mixture N1 plus N2 gamma minus 1 N1 gamma minus 1 N2 gamma 2 minus 1. Like this, the gamma of a mixture also we can define. Then total energy will be sum of energy due to individual gases. N1 F1 RT by 2 N2 F2 RT by 2. Like this will define the total energy of the gas. Then what about the total pressure? The total pressure will be sum of pressure due to individual gases. N1 RT by V N2 RB. What do you mean by N1, N2? Number of moles. And both will occupy same volume. We should not write V1. No, both the gases will occupy the same volume. This is nothing but the Dalton's laws of partial pressure. These are some related to mixture of gases. Next we have the rate of collisions per unit. These molecules they'll be colliding with the wall. How many collisions per second per unit area? It depends upon the temperature, molecular mass of the gas, then volume of vessel. And the number of moles. So as the temperature increases, more collisions will take place. There's a basic idea of the rate of collisions. So how temperature increases, rate of collisions will increase. As number of moles will increase, rate of collisions will increase. So for that, let me explain here. This is a vessel. Now we'll introduce the number of molecules. Some collisions are taking place. Okay, fine. At a given temperature, some collisions are taking place. Now I will increase more number of molecules. Definitely more number of collisions. So definitely rate of collision per unit area depends on number of molecules. Okay, I agree this one. As we rise the temperature now, you can see the number of collisions per second per unit area will increase. No, they are colliding with more rapidly, more number of collisions taking place as I decrease temperature. As I decrease temperature, will be less. You can see clearly, number of collisions will be less. Agreed. Their RMS speed will also decrease and number of collisions also will decrease here. This is at lower temperature. As I increase temperature, then number of collisions will increase. There's one basic idea about the conditions. So as I increase temperature, you can see that the number of collisions is increasing. I'm increasing the temperature. No, I'll decrease the temperature. No, number of collisions will decrease. So the rate of collision depends on amount of gas and also the square root of temperature. That's one basic idea. Okay, fine. So this particular formula you have to remember here. Next we have the mean free path. Total distance traveled by gas molecule between successive collisions by total number of collisions. So this particular thing we can call that as the mean free path. Suppose a gas molecule will collide. So this will move a distance x1, x2, x3, x4, x5, x6, x7, x8. Then lambda will define like this. So on xn by total number of collisions. There is one formula which you have to remember, which will be very useful. To give the temperature of gas, they will express this particular basic condition. This is about the theoretical ideas of the KTG. Next, we'll explore some exam-oriented content here only. It's not yet over. Now there is a vessel where there is a piston. The molecules will be moving random, they'll collide, and the net resultant force exerted molecules per unit area will balance this pressure force. Here the weight of the piston m1g will act. The pressure force will act here. Directly you can bring it here. Then atmospheric pressure force P0. The number of moles here will write like this: P1 volume V1 equal to nRT1. What is the pressure? Here who will balance the pressure force of the gas? The resultant force exerted by the gas molecules on the piston is called as the pressure force. So this will become P1A minus P0A minus M1G equals 0. Or P1 equal to, how much it is? P0 plus mg by, we'll write it here, P0 plus mg by, what is the volume of gas? Al1. Number of moles as it is. We'll get temperature. I have introduced load. I'll keep some load. I'll add some more load. Then what are the weight of the piston? Weight of the load. Pressure force P0A. Now the pressure of gas will increase. Its volume also changing. Now what is the new equation will be? P2A. Who will balance this weight of the piston and the load? These two are. So P2A minus P0A minus M1G minus M2G 0. Or P2 equal to P0 plus M1G M1 plus M2G by A. Again, we'll apply ideal gas equation. P2 V2 equal to N0 T2. Now the temperature of gas will be T2. What is P2? P0 plus M1 plus M2 G by A. What is the volume of gas? AL2 equal to N0 T2. Like this, we can calculate the unknown things. What will happen to rate of collision? Rate of collision directly proportional to Fn1 will become N1 root T1. Number of molecules will be same. Rate of collision Fn2 equal to N T2. Or it will be Fn root of T1 by T2. Better remember like that. For a given gas, no, number of moles will remain same. Number of moles, amount of gas will not change. Then based on the if temperature increases, then rate of collisions will also increase. The pressure force of gas is something very important. Here we have the condition like this. The weight of the piston will act. mg, air is present, air will exert atmospheric pressure for P0. The pressure force of gas will be Pa. Number of moles, let T be the temperature. Then who will balance this one? Pa plus mg minus P0. What is the pressure force of gas? Will be P0 minus mg by. If I know the height h, then PV equal to nRT. Pressure force P0 minus mg by A. What is the volume? Volume of the gas will be, let A be the area of cross section. A into H, nRT. What is N? N is the number of moles. The mass of gas will be negligible compared to what are these molecules? They'll be moving random, they're colliding. The molecules are colliding. Because of that, this pressure force will come. Now we have to calculate the compression in the spring. There's a gas, and these molecules will be moving. They'll be moving towards right. They'll go and exert force of these gas molecules, and this is the pressure force. P. Outside that air will exert force. Atmospheric pressure P0. Here also air molecules are present, and let the spring be compressed. Kx. Let the T be the temperature. Let L be the length. Let A be the area of cross section. So now this is spring. What is the equation we can write for equilibrium? Pa minus P0A minus Kx. K is the spring constant. X is the compression in the spring. Then what is P equal to nRT by volume. P0A minus Kx equals 0. nRT. T is the temperature of gas. What is the volume? Volume will be A by L. Like this we can calculate the compression. nRT by AL. Here one A is missing. nRT by L plus P0A all divided by K. Now this will become nRT P0AL by K. Means the pressure force of gas, can it balance the weight? Can it act for equilibrium along with the spring? This is one pressure force of gas is what you have to develop. This is what I'm interested in. Pressure force of a gas. An idea I am trying to generate. Where all you see gas, not only on the piston, it will exert force on the walls also, here also, everywhere. Here also we can write it. Not only at one point, at all several points it will be exerting. This is a basic condition. Now there's a left vessel contains monatomic gas at temperature T, pressure P1. The right vessel contains diatomic gas at pressure P2, temperature T2. Volume of the vessels are V1 and V2. There's a valve, non-conducting to. I'll open the valve. The gas will flow from higher pressure to lower pressure. Heat exchange will occur, and also diffusion also will take place. How to calculate the pressure and temperature at equilibrium? This is a question. Then to calculate the temperature, I should go for the energy conservation. Initial energy should be equal to the final energy. Initial energy of this chamber is U1, U2 into energy. Final energy will be U1 dash, U2 dash. Then what about the initial energy? N1 F1 R T1 by 2. N2 F2 R T2 by 2. Final energy N1 F1 RT by 2. N2 F2 RT by 2. Number of moles will not change. So the final temperature will be like this, temperature at equilibrium. Then to get the temperature, we should use the energy conservation. To get the final pressure, the amount of gas remains same, or the mass of gas remains same, or number of moles will remain same. What is N1? N1 will be here P1 V1 RT1, N2 P2 V2 by RT2. Final pressure P V1 RT, P V2 RT. Then this will become P1 V1 T2 P2 V2 T1 by T1 T2 into V1 plus V2 by P. So substitute the value of T here, then solve for P. Like this we can calculate the pressure at the equilibrium. To get the pressure, you should use this formula. To get the temperature, use conservation of energy principle. This is the amount of gas, conservation of mass. And this is conservation of energy. Okay kids, this is about the KTG. These are small ideas, some maxims, some formulas are there. If you remember, more than sufficient. It's a very simple topic and very good number of problems are being asked. Okay kids, we'll continue with the dissociation of gas molecule. If there are there's a nitrogen, 12 moles of nitrogen gas is filled up in this vessel. It's a diatomic gas. Then in that 1, 2, 3, 4, 5 moles will break up. 5 moles will break up. Break up means dissociates. Then what will happen to the new pressure? The earlier pressure was P. What was the earlier pressure? nRT by V. What is then N12RT by V? The new pressure, the total pressure will be pressure due to nitrogen atoms, pressure due to the nitrogen molecule. How many atoms are there? Number of moles. Actually here 5 moles will break up. 1, 2, 3, 4, 5. So here 10 into NR, okay, 10 R T by V. How many left over? 7 will be left over. 7 RT by V. So 17 RT by V. This will be the new pressure. So definitely what will happen to we have to supply energy on its own, not possible. We have to supply energy. So what is energy supplied equal to change in internal energy. Internal energy U dash, this is U. This is equal to number of moles. Number of moles will be here 10 degree of freedom 3R by 2 into temperature. Then how many moles left out? Because 5 nitrogen molecules where they break up, 10 nitrogen atoms will be generated. The remaining 7 will be as it is. 7 into 5R by 2 T. There's a final energy. Initial energy will be 12 5R by 2 into T. You check it, this will be 15 RT. 37 to, okay, this will be 7 5 is 35. 35 by 2, 17.5 RT minus 30 RT. Okay, 15, 15, 30, 32.5 RT, this 30 RT. So how much of energy you have to supply? Energy to be supplied. Okay, fine. There's one basic method of this one. If they give some information about mass, suppose like a m amount of gas is present. In this 30% will break up and the remaining 70% as it is. Is a diatomic gas. Monatomic, diatomic. There's a diatomic gas. In that 30% will dissociate 70% as it is. Then the new pressure will be N1. What is the N1? N1 RT by V. N2 RT by V. What about N1? N1 will be number of moles. Now, number of moles, what you can at mass, no? 30% of that will become. So 0.3 into 2 total mass M by molecular mass RT by V. The next remaining 70% as it is 0.7 mass M by M naught RT by V. If they give information about the mass of gas, of which 30% will dissociate, remaining 70% will be as it is, then this is a method you should apply. What is the molecular mass? Molecular mass will become off, no? That's why we should write, actually it is like this. Diatomic gas, when break it up, its molecular mass will become off. Why 0.3? 30% will dissociate. And whatever the pressure will be due to these two. These are small ideas of KTG, very, very simple and important. You're supposed to learn. Mixture, I fill up both monoatomic and diatomic gas. What is the total pressure? Total pressure will be pressure due to monoatomic gas and pressure due to diatomic gas. What is the pressure due to number of moles? R T by V. Both monoatomic and diatomic gas will occupy the same volume. N1 is number of moles of it. Similarly, diatomic gas N2 RT by V. This is the pressure. The intensity will be N1 F1 RT by 2 plus N2 F2 RT by 2. N1 F1 will be 3. N2 5 RT by 2. This is the intensity. Then ratio of rate of collisions. This will be directly proportional to N1 Avogadro number RT by 3M naught. They will have different rate of collisions. The number of collisions by the monoatomic and diatomic gas will be different. These are all things. And what about the average kinetic, translational kinetic energy? Average translation of both monoatomic and diatomic will be same. How much it is? 3 by 2 kT. Total energy will be different. Monoatomic gas, how much it is? 3 by 2 kT. For diatomic gas, it will be due to translational and due to rotational, 5 by 2 kT. So for any gas molecule, the average translational kinetic energy per molecule will be 3 by 2 kT. Per mole it will be 3 by 2 RT. Now these formulas you should remember, very very important. Just will summarize it. Average translational kinetic energy will be 3 by 2 kT. This is per molecule. This is per mole. Next we have the Gauss law. What is the Boyle's law? So this is the temperature remaining constant. Then there is a cylinder of mass having a piston of mass. Inside is what? We have the gas molecules. These are the gas molecules. Inside we have the gas molecules. The gas molecules will collide with the piston, and the weight of the piston is balanced by the pressure force of the gas, where pressure force of gas is mg by a. Now I'll expand this gas. The volume will increase. So here it is. We have the gas law. The first one is Boyle's law. Temperature remains constant. There is a cylinder filled up with a gas, closed with a piston, and mass m0 is placed. We will balance the weight of the piston and weight of the block, the pressure force. The pressure force P1A equal to mg plus m0g. P1 equal to mga plus m0g. This is the pressure of the gas. Volume of the gas, let it be V1. I'll remove this load. When you remove this load, the gas will expand. Then the pressure will decrease. What is the new pressure will be? mg by a. Then we can write P1 V1 equal to P2 V. Temperature of gas remaining constant. This is what practically we have to do. Like this what happens. Next is Charles law at constant volume. Next we have the Charles law at constant volume. I'll increase the temperature. So how to increase the temperature? I'll supply the heat. By supplying the heat, the gas will absorb it, temperature will increase, and proportionally the pressure will increase. Volume of the gas will remain constant. Then here we'll get P1 by T1 equal to P2 V2. This was the basic, the Charles law. Right? So here we are supplying the heat. Charles law at constant volume. Now similarly, Charles law at constant pressure. Here, as I increase the temperature, the volume will increase. How that particular volume can increase? By making pressure constant, we'll take the same diagram. Next we have the Charles law at constant pressure. Here we'll supply heat. The piston will start moving up. The gas will start expanding. Then as I supply, the temperature increase, the volume will increase, the pressure remains constant. So this is the basic mechanism. You see the volume, the piston will start moving up. As it starts moving up slowly with a constant speed, the volume of gas will increase. As the temperature increases, the volume will increase. Then what will happen to the pressure of gas? Remains constant. This was the basic Charles law. Then we can have a situation where all three are variable. All three. P1 V1 N RT1, P2 V2 N RT2. As it is possible, I supply it, temperature will increase, volume will increase, pressure will increase. Or pressure will decrease, volume will decrease. So anything, all three can be variable. Any two are variable, one constant, or all three are variable. This is what basically happens in the case of the gas laws. In moles of ideal gas, if you fill up in a vessel, temperature can be constant, pressure can be constant, volume can be constant, and all three can also be variable. There's a general idea, try to develop. Okay, now we'll discuss the first law of thermodynamics. We are going to enter into the concept of thermodynamics. Then I'll supply heat to the gas. The gas will expand. At the same time, the gas is able to lift this piston. This piston is having mass. Or here I'm bringing a better diagram here. I'll supply heat. There's a pressure force of the gas. Pressure force of the gas is how much? P1A. Then you can see this, the pressure force of the gas. It is able to displace the piston. No? It is able to do work. It is able to lift the block. This particular block is having mass m. Look at the kinetic potential energy of the block got increased. Who has lifted this block? The pressure force of gas. Inside here, the gas molecules are present. What these gas molecules? They will be colliding here. So what we should assume here? These are n moles of ideal gas. This assumption should be there with you all the time. Huh? And what these molecules? These molecules only will lift this particular block. So therefore, who is responsible for the displacement of the block? This gas only. So the pressure force of gas is able to do work. I supply heat. The heat supplied by it will be converted into rise in intensity plus work done. This is a work done by the gas. What do you mean by this? Heat supplied. Heat exchange, you can call it. Delta U, rise in or change in intensity. And this is work done by gas, work done by the gas. All these are nothing but conservation of energy principle only. What is first law of thermodynamics? It is nothing but conservation of energy principle only. The heat supplied, a part will be converted into increase in kinetic energy of the molecules. The remaining is what? Mechanical work done. Work done by the gas. This is better you call mechanical work done by gas. There's one basic condition. Huh? This was the first law. So what is the change in intensity? It is nothing but increase in kinetic energy of molecules. Mechanical work done. This can be rise in gravitational potential energy of the block or increase in kinetic energy of the block. Any other thing, it can mechanical work. This is heat supplied. So nothing but there is a conservation of energy principle only. No? This is basic. So we'll discuss in detail all these terms. So what is Q? So when heat supplied, one by one all the terms will define. Heat supplied. Symbol will be Q. Then if gas absorbs heat at constant pressure, NCP delta T. If it absorbs heat at constant volume, NCV delta T. Where Cp minus Cv equal to R and gamma equal to Cp by Cv. Then what is the Q? Heat is absorbed when a gas absorbs heat. Gas absorbs heat. Q will be positive. Gas rejects heat. Q will be negative. This is a sign convention what you can follow. Similarly, the change in intensity. So next one will be change in intensity. We'll discuss here. What is the change in intensity? Change in intensity should be delta U equal to NCV delta T or NR gamma minus 1 delta T or NF R delta T by 2. These are formulas. Further, this will become NR gamma minus 1 T2 minus T1, and it's a change is a state function. Internal energy is a state function and is dependent on only initial and final states, is independent of path. This is about the intention is what you should remember. These are the formulas. In any process, NCV delta T. In any process, you can use this formula, NCV delta T only. Then next we'll take the work done. All the terms we'll discuss in detail. I have don't have place. I'll work done. Then the gas. If we will take the some small concept. There's a piston. The gas molecules which are present here, they'll exert a force, and the pressure force is PA, that one, and let this be mass here. After some time, the piston will undergo displacement. So if it undergoes displacement here, then work done by the gas will be dW equal to F into dx. What is F? Pressure force. Then dW, A dx will become area of cross section of piston here. M is the mass. This A into dx will become change in volume. So therefore work done equal to integral of P dV. So this will be area under PV graph. In any process, work done by gas, integral of P dV. The gas is having ability to do work. Okay, so this work done by gas, what will happen to it? Will be converted into increase in kinetic energy. This will start moving up because when force acts, body will accelerate. Due to acceleration, the piston, when it comes here, will have velocity v. Okay, like this will be the work done by the gas. Like this, we'll discuss the problems. Then, what do you mean by when work done? If the volume of, here you can see the compression will occur. The piston was here and it has moved. So the displacement was downward. Then work done by gas. If work is done on the gas, so therefore work done will be negative or volume decreases. Simple. Similarly, the gas will expand. Here who will compress? The gas will compress. Here gas expands. Gas is compressed. Okay, fine. Now the gas will expand. The piston will move. The displacement of piston is upward. Here work done will be positive. Here volume increases. So what is the basic method? If the volume of gas increases, work done by gas positive. Volume of gas decreases, work done by gas is negative. No need of anything, just remember this. Then we'll go for some graphical thing. Cyclic process, any shape. It need not be circle, any shape. No, I'll start like this. There's a pressure, there's a volume, there's a volume, there's a pressure. Then there's a clockwise cyclic process. There's a counterclockwise cyclic process. Okay, fine. What about the work done? The work done. Now we'll start like this. Let this be pressure, be P2, V1, V2. Then this will be, we'll define this as radius. Then what is the area under PV graph? Pi r square, pi r into r. 1r is P2 minus P1 by 2. Other r is V2 minus V1 by 2. There's a work done by the gas, and this will be positive. Work done by the gas will be positive when it is clockwise. Work done by the gas will be negative when it is counterclockwise. Then here also the same formula. The work done by the gas, again the same formula. Minus P, P2 minus P1, V2 minus V1 by 4. Why negative? Counterclockwise. Clockwise cyclic process, work done positive. Counterclockwise will be negative. These are the first law of basic thermodynamics is what you should understand. And work done is independent of path. No, this is about the work done. We'll discuss in detail about all the three quantities we have studied here. So first we'll go for the work done. Work done along the path AB. Work done for the path AB. This area under the curve will be more than this, so this will be greater than B than greater than C. Then what is change in intensity? Change in intensity will be same for all the path. Change in intensity will be same. What about Q? Q will be delta U plus W. So Q1 so like this heat absorbed will be different for different parts. So which one is independent of path? This one. Change in intensity. Independent of path. What about this? Dependent on path. This also depends on path. Just directly use the formula. Nothing is there. Q equal to delta U plus W. If you know delta U, W, you can get the Q. We discuss the reversible, irreversible process. A very conceptual, very simple, just a basic idea. Suppose ice cream is there, it will melt and it will get formed the liquid. Yet the same ice cream substance, it is there in the form of solid. When it melts, it will become liquid. Again you freeze it. So again if you start cooling it, it will get freeze, again will get ice cream. So this is a reversible process. Similarly, ice is there, ice blocks, you melt it, will become water. Water you freeze it, will become ice blocks. This is called like a reversible. Irreversible, what do you mean by irreversible? Irreversible means, suppose a wood is there, you burn it, will get the charcoal, fire. From fire you don't get back the wood. This is called like a irreversible. Getting some idea? Like this in thermodynamics also, will be having the reversible and irreversible. What do you mean by reversible? Suppose that there's a pressure, there's a volume, the gas will expand. Again, if it undergoes compression, the pressure volume should vary in the same way. This is called like a reversible process. Irreversible process will be like this. It will not follow the same path. All the process will be irreversible only. All the process that occurs, this is reversible. This is irreversible. All the processes that occur will be irreversible only, not reversible. Practical because of friction, because of dissipative forces. This is ideal. This is practical. We'll discuss only ideal. Our thermodynamics will be ideal. We'll assume that no dissipative friction force is available. The friction between the piston and cylinder will lead to irreversible process. All our things will be reversible only. This is ideal. Suppose the gas will expand. The same water and the gas, if you compress it, may not follow the same path. May reach somewhere here. So these are also things we have to supposed to remember. Next we have the isothermal process. The gas will undergo isothermal process. The temperature remains constant. What is the basic idea? Isothermal process. Temperature of gas remains constant. Then according to the formula, P1 V1 equal to nRT, P2 V2 equal to nRT, or P1 V1 equal to P2 V2. The temperature of gas remains constant. Pressure, volume, they are going to vary. The gas will expand at a constant temperature. What is actually isothermal process? Means I supply heat. How do we supply heat? Anything? There's a heat I supplied. Heat I can supply through the candle or through the flame, any of the method. There's a heat supplied. And what it will do with this heat? It will convert into work. Because delta U is 0. Because if T constant, delta T 0. If delta T 0, delta U will be 0. So Q equal to V know delta U plus W, which is equal to 0 plus W, Q equal to W. So what this isothermal process directly converts heat into mechanical work, or mechanical work into heat. Any amount of heat will convert into mechanical work. Any amount of mechanical work will convert into heat. Then area under the curve should be equal to heat absorbed. So in isothermal expansion, work done we know equal to P dV, volume V1 to V2. This will become, or V final, V initial, P equal to nRT by V. There's a work done or heat absorbed. In isothermal expansion, it is absorbed. In isothermal compression, heat will be rejected. So what is isothermal process? Converts any amount of heat into mechanical work. So if you push the piston, work will be converted into heat or heat into work. This is the basic idea. So what is the isothermal process? Heat is converted into mechanical work. We'll discuss some graphical things. Now, if you look at the graph here, all possible graphs we'll discuss. Next, the pressure versus P volume graph. This will be rectangular hyperbola. Okay, fine. This will be rectangular hyperbola. Here V1, this will be P1, this will be P1. Okay, fine. And this will be the rectangular hyperbola. What about the pressure temperature graph? It should be constant because temperature constant. Temperature volume graph, temperature should be constant. The next, pressure and density graph. We know isothermal process, PV equal to nRT. Number of moles will be mass by molecular mass, P equal to rho RT by M naught. So RT, M naught are constant. So pressure will be directly proportional to the temperature, density. So this will be the isothermal process. Try to remember all these graphs. Huh? Next graph will be internal energy versus density graph. Internal energy, nothing but the temperature. Reciprocal of density will be volume. So then now the graph if they should be horizontal. Because the temperature constant means intensity will be constant. So these are some ideas for the isothermal process. Background, this is very, very important. With this you can manage the problem solving. Next one we have the adiabatic process. It's a process where no heat exchange. Then Q equal to delta U plus W, Q0. Okay, this is a work done by the gas. Fine. Now after this, what about the process here now? So how actually it happens here now? If you look at the particular, there's a piston. It is in this position. Call length L1. I'll move the piston downward. And there's no heat exchange. I'll do work. Then what will happen to it? The temperature of the gas will increase. T2 greater than T1, V2 less than V1. Similarly, P1, P2. P2 greater than P1. I'll move the piston downward. I'll just press it. Then the gas will undergo compression. The pressure will increase, volume will decrease, the temperature will increase. So it's a process where all three are variable. This is what happens in the case of the adiabatic process here. Then they are related by this equation. PV gamma equal to constant. Similarly, TV gamma minus 1 equal to constant. Then P1 minus gamma, T gamma will be constant. So these are the pressure temperature where gamma will be Cp by Cv, Cv equal to Fr by 2 and Cp minus Cv equal to R. Like this we can calculate the gamma for monatomic gas. Gamma will be 5 by 3. For diatomic gas, gamma will be 7 by 5. Like this, try to remember it. The pressure volumes, they are related by this equation. So what do you mean by adiabatic compression? Pressure and temperature increase. What do you mean by adiabatic expansion? I'll move it, the piston is shifted up. Here the pressure and temperature will decrease, volume will increase, the pressure temperature will increase here. So this will be the adiabatic expansion, this is adiabatic compression. So these are the general things. Here it is undergoing the expansion, you can see that one. The volume will increase. And the curve is not rectangular hyperbola related by this particular basic equation. So what this adiabatic process, it will convert mechanical work into rise in energy or vice versa. So then we can bring the formula work done by the gas. Work done by the gas, we can write it as this will be Pi Vi minus Pf Vf by gamma minus 1. No heat exchange. So here if the gas undergoes compression, intensity increases. Here work done by gas in adiabatic compression, what actually happens? Work done by the gas negative, delta U positive. In adiabatic expansion, work done by gas positive, delta U will be negative or decreases better, intensity decreases. Here intensity increases. These are some ideas you have to remember for adiabatic process. Next, isothermal expansion, adiabatic expansion. For the, we know PV equal to constant for isothermal. Then differentiating this, dP by dV equal to minus P by V. Similarly, PV gamma differentiating this dP by dV equal to minus gamma P by V. dP by dV. So the slope of the adiabatic curve will be slightly greater than that of the isothermal expansion. Why? Because gamma factor is coming. Okay, with this. Similarly, here gamma for monoatomic gas. For different types of gases, gamma will define it. Monoatomic gas, gamma will be pi by 3. Diatomic gas, triatomic gas, (7 by 6). So definitely gamma for monoatomic gas will be greater than that of triatomic gas. So the slope for monoatomic gas should be more than that of diatomic. So this will be the monoatomic, this will be diatomic, this will be triatomic. So this gas will be monoatomic, this will be diatomic, this will be triatomic. So like this, by calculating slope we'll get the gamma. From there we can determine the the characteristics of the gas here. And there are some small basic ideas. Similarly, we'll define the bulk modulus of the isothermal as well as adiabatic process. I'll discuss that later on in detail. We'll discuss in detail. Further, when we discuss the molar capacity, there I'll explain some very important things. Next, we have the isobaric process. It's a process where pressure will be constant. Pressure will be constant. PV equal to nRT. So P1 V1 nRT1 equal to P2 V nRT2. So like this we can write P1 by T1 equal to P2 by T2, or P by T will be constant. This is a isobaric process. The pressure will remain constant. So from the graph also we can write it here. PV graph. The pressure remaining constant. There is V1, V2. This will be the work done by the gas. The area under this will be the work done by the gas. So there's one basic assumption. How pressure will remain constant. The volume increases, how pressure will remain constant. So this will try to explain here now. Now the weight of the piston will act here. P equal to P naught plus mg by the initial volume, this will be the final volume. Or V2, V1 will write it. Temperature T1, T2. Look at the pressure, pressure will be constant. I'll supply heat here. What all we supplied it, a part will be used to rise the intensity, remaining is utilized to do mechanical work by the gas. So here Q equal to delta U plus, what is work done by the gas? Work done by the gas should be equal to P into delta V. P into delta V will be NR delta T. And further, NR delta T we can write it as gamma minus 1 delta U. Q equal to gamma delta U. There is one formula. Similarly, delta U I can replace it as NR delta T gamma minus 1 work done by the gas. NR delta T will become P delta V. P delta V will become work done by the gas. Gamma by gamma minus 1. This is one basic relationship. In case of isobaric process, what all we supply it, all heat will not be converted into work done. A part will be converted into rising temperature, remaining converted into work done. Able to understand now? And this further we can write Q equal to NCP delta T, where Cp is the molar specific heat at constant pressure. This is about the heat exchange formula, sir. Next, various graphs. In PV graph will be horizontal line. In PT graph, isothermal, it will be isobaric heating. Isobaric heating again it will be horizontal line. Pressure should be constant. VT graph, straight line passing through origin. Isobaric process. In intensity versus density graph, we know PV equal to nRT. Pressure constant. So volume number of moles will become mass by molecular mass. P equal to mass by volume RT by m naught, which will become P rho RT by m naught. Then on the other side we know intensity will be N F R T by 2 or NR gamma minus 1, NRT gamma minus 1. So this RT I can replace no in terms of gamma. This will become rho m naught. RT will become U gamma minus 1 N. So this will become P1 pressure will be constant. So therefore this U rho will be constant. U rho will be P m naught and gamma, all are constant. So therefore U will be inversely proportional to 1 by rho. So therefore this will be rectangular hyperbola. Very, very important. Isobaric process, intensity versus density will be rectangular hyperbola. This is about the basic isobaric process. Isochoric process, the volume of gas remains constant. Pressure P1, temperature become T1, T2. Volume will be constant and the work done by the gas will be 0. What all we heat supplied will be Q equal delta U, which is equal to NCV or NR gamma minus 1 T2 minus T1. This will be the heat supplied. Then P1V equal to nRT1, P2V equal to nRT2, P1 by T1 equal to P2 by T2. VT graph first PT graph will plot it. Straight line passing through origin, PT graph. Then next again Euro graph, intensity versus density. This will be a straight line, vertical. Why vertical? Volume constant, density will be constant. And then what about the PV graph or volume pressure? Horizontal line. These are all isochoric process, work done 0. What all heat supplied will be converted into change in intensity. If you supply it, the intensity of gas will increase. If you take out heat, the intensity of gas will decrease. So work done by gas will be 0 or nothing but in a fixed, like a rigid container, a rigid vessel, whose volume will remain constant. Then you fill up gas and supply it, the gas will absorb it, nothing but here it will undergo isochoric process. This is the one generalized idea which you have to develop here. We will discuss the heat engine and efficiency of gas in one full cycle. Heat is absorbed. Engine. What engine? Engine contains n moles of ideal gas. It contains n moles of ideal gas. It is supplied to ideal gas. It is made to undergo the cyclic process. So here heat supplied is equal to mechanical work done by the gas plus heat rejected. Okay, this is Q1 equal to work done by gas equal to. Then how we define efficiency? Efficiency is defined by output, mechanical or say work done by the gas plus heat absorbed. Or I'll do one thing. Mechanical work by net heat absorbed. Net work done by the gas by net heat absorbed. Net heat absorbed will be Q1. So this will become Q1 minus Q2 by Q1. So this will become 1 minus Q2 by Q1. This Q1 is what we'll call net heat absorbed. This is a net work done by the gas. Net heat rejected. So this will become efficiency 1 minus mod of heat rejected by heat absorbed. Like this. Why mod means? Because heat rejected will be negative, no? So therefore we are using this formula, or else you can go for the other one. Net heat absorbed. Either of the formulas you can. And for cyclic process, what is delta U for cyclic process? Change in energy 0, that one. So what all heat absorbed, a part will be converted into work done, remaining will be rejected as heat. We discussed several cyclic processes. There is a 1 mole of monatomic gas undergoing cyclic process. We have to calculate the efficiency. What about 1 to isochoric process? So isochoric heating, ET is absorbed here. 2, 3 isobaric. So isobaric heating. 3, 4 isochoric cooling, ET is rejected. 4, 1 isobaric cooling, heat will be rejected. Fine. Now we have to calculate the efficiency. So area under the graph will give the work done. It's a clockwise cyclic process. Net work done will be positive area under the graph. So what is the net work done by the gas? Should be equal to area 3P0 minus P0. 2V0 by area of rectangle. So 2P0 V0. Then where all heat is absorbed? It is absorbed in the this Q12 and Q23. Because how you define efficiency? Net heat absorbed by the net work done by Q positive. The efficiency. So what is the Q positive? Heat absorbed in the isochoric process and heat absorbed in the isobaric heating. In isobaric process, in isochoric process, heat absorbed. Change in energy, NCV delta T. In isobaric process, what is the heat absorbed? NCP delta T. Number of moles 1, 3R by 2, CV for monatomic gas. Change in temperature, T2 minus T1. This will be 5R by 2. CP will be 5R by 2. T3 minus T2. This will become 3R by 2. T2 temperature 3P0 V0 by R. T1 temperature P0 V0 by R. T3 will be 6P0 V0 by R. 3P0 V0 by R. 3P0 V0. This will be 15P0 V0 by 2. So the efficiency will define as net work done by Q positive. So 21 P0 V0 by 2 by 2 P0 V0. So 21 by 4. It will be less than 100%. This is the one way of calculating the efficiency. Then we'll plot also the equivalent graphs. Now what are equivalent graphs? First graph will be a PT graph, pressure versus pressure temperature graph, rough graph. Isochoric heating, pressure volume constant, the pressure increases, the temperature increases. So will be like this. Then isobaric heating, then isochoric cooling, straight line passing through origin. Next, isochoric cooling. VT graph. So isochoric heating, volume isochoric heating, so it will be like this. Then isobaric heating, Isochoric cooling. Okay, this is a PT graph to PV graph. So this will be isochoric. Here only I'll write it. This is isochoric heating. Isochoric heating. This is isobaric. Like this, you have to identify the process. This is isochoric cooling. This isobaric cooling. And the basic formulas you must know. NCV delta T. Heat absorbed in isobaric process will be NCP delta T. In isochoric process, NCV delta T. Okay, kids, we have the problem. Find the efficiency of gas in one full cycle. Pressure versus temperature graph. So we have the curve here like this. 1, 2, path 1, 2 is isobaric process, isochoric. And this will be isothermal. This will be isochoric process. So what is 1, 2? 1, 2 will be isobaric heating. So heat will be absorbed. And 2, 3 isothermal compression. Heat will be rejected. And 3, 1 will be isochoric cooling. It will be rejected. Temperature it will be rejected. So first we'll indicate one thing. What about 1, 2? 1, 2 will be isobaric heating. What about 2, 3? 2, 3 will be isothermal expansion. And what about 3, 1? 3, 1 will be isochoric cooling. Then the efficiency will define 1 minus Q negative by Q positive. What is the Q negative? Where all it is rejected, Q31, Q323. And where all it is absorbed, it is absorbed only in the path 1, 2. So we'll calculate them. So this will be Q1, Q positive. Will be Q12. What is Q12? Isobaric heating, monoatomic gas, NCP T2 minus T1. Number of moles 1. Monoatomic gas 5R by 2, 2 T0 minus T0. 5R T0 by 2. Heat rejected will be Q23 plus Q31. Q23 isothermal compression. NR temperature 2 T0 log of final volume by initial volume, or final pressure, initial pressure by final pressure. Q23 isochoric cooling, NCV T1 minus T3. Q negative, this will be 2R T0 log of P2 by P2 will be P0, this will be 2 P0 plus CV 3R by 2. T1 minus T3. T2 minus 2 T0. So this will be 2R T0 log 2 minus 3R T0 by 2. So then the efficiency will be Okay, now you got the idea why modulus should be there. 1 minus mod of minus 2r naught log 2 3r t naught by 2 by mod of q positive 5r t naught by 2. Solving this will be r also get cancelled, so 2 log 2 plus 3 by 2 by 5 by 2. This is efficiency. Any process you can find out. Okay, sir, how you plot the graph? Can you help us in plotting graphs? We will plot the graph one. I'll use this space here only. Just have patience. Screen space actually will be very small. In a highly congested way, I have to manage everything. It's not that easily. In a very less space, I have to write down. A lot of difficulties I'll be having here. It's not that easy online teaching also. Okay, first we'll go for the PV graph. These are very important. These are the types of questions what you can expect in exam. Then this will be pressure P, volume V. Isochoric heating, isobaric heating. Volume will increase, pressure will be constant. Put it like this, the curve. Then isothermal expansion, isothermal compression. Isothermal compression means volume will decrease. Then isochoric cooling. This is the graph. 1, 2, 3. Okay, sir, can you plot the VT graph, volume temperature graph? Volume constant. Sorry, volume constant. Isochoric process. Isochoric, like a eating it is. Sorry, isobaric. Isobaric process, no? Isobaric process. Volume will increase, so it will be like a straight line. Yeah, fine. Next, afterwards, isothermal compression. Then isochoric cooling. These are the graphs. This will be point 1, 2, 3. Okay, earlier PV graph, PT graph. Next, I'll take the VT graph and we'll discuss one problem. And there's a volume temperature graph. We have to calculate the efficiency of gas in one full cycle. There's a volume versus temperature graph. It's a cyclic process 1, 2, 3, 4, 1. We have to calculate the efficiency. Where all the ET is absorbed. It is absorbed in the path 1, 2. Isochoric heating it is. 2, 3. Isobaric heating. It is absorbed. Isochoric cooling. It is rejected. Isobaric cooling. It is rejected. So what is 1, 2? Path 1, 2 will be isochoric heating. Then similarly 3, 4 will be isochoric cooling. Then path 2, 3 will be isobaric heating. Path 4, 1 will be isobaric cooling. Now first identification of path, then Q positive, where all it is absorbed in heating process. Q1, 2 plus Q23. 1 mole of in isochoric process NCV T2 minus T1. In isobaric process NCP T3 minus T2. Number of moles 1, so 3R by 2 T2 minus T1, 5R by 2 T3 minus T2. Where all ET is rejected, Q34 plus Q41, Q34, NCP T4 minus T3, NCV T1 minus T4, T4 as it is this temperature, so keep it. This will be 3R by 2. Then efficiency, how you define? 1 minus Q negative by Q positive. Substitute this will become 1 minus Q negative. T4 will less than T3, T1 less than, so this will be 5 T4 minus T3. There's the efficiency. Substituting all these values, we'll get this one. Then, so okay, sir, how you plot the graphs? Can you show the plotting graphs? First, the PV graph. Pressure versus volume. Isochoric heating. Isochoric heating. Isobaric heating. Then isobaric cooling. Then isobaric cooling. Then this will be 1, 2, 3, 4. There's a VT graph, there's a PV graph. Then volume temperature graph. Pressure temperature graph. Then isochoric process, isochoric heating should be straight line passing through origin. Then isobaric heating. Then isochoric cooling. Then this is a graph. This will be 1, 2, 3, 4. This is a PT graph. Now you have to understand things. 1, 2 problems you understand, you can manage. So this is about the typical questions what they'll ask you for JEE Mains Advanced. We'll define first the molar heat capacity, which is equal to heat absorbed per unit mole per unit rise in temperature. Symbol will be, this will be Q and delta T. In the differential form, it will be dQ by N dt. Then further, we know dQ equal to du plus dw. C is equal to du plus dw N dt. Du by N dt plus dw by dt. Or this will become C P dV by dt. And there is a generalized formula which you can remember. Then we'll do one thing. First, we'll make a list. some different types of processor. The process here will take constant and molar capacity we'll discuss. Then isothermal process. Temperature will be constant. We know for isothermal process, temperature dT constant. dT will be 0. Then molar capacity will be, or select here, delta T will be 0. Then molar capacity will be infinity here for next adiabatic process. In adiabatic process, heat exchange itself will be 0. Parameter will write it better. dq, no heat exchange. So molar capacity for adiabatic process will be 0. For isobaric, pressure will be constant. Then C isobar will be equal to Cp. Then for isochoric process, volume will be constant or work done 0. Then molar capacity for isochoric process will be equal to Cv. For different process, molar capacity will be different here. Molar specific heat capacity. For solid liquids, it will be fixed value. For a given n moles of gas, for different process, it will be different. Same. You can take hydrogen, 1 mole of hydrogen. Same 1 mole of hydrogen will have different molar capacity for different process. Similarly, for polytropic process, what is the polytropic process? PV to the power of x equal to constant. It can be anything. Then the molar capacity is given by Cv R1 minus x. Then work done by the gas equal to nR delta T in such a process given by 1 minus x. Okay, done. Like this, we can define the molar capacity. Similarly, we'll define the bulk modulus. What is B? Bulk modulus. How we define bulk modulus? Minus dP by dV by V. And I'll bring it separate. For isothermal process, PV equal to constant. PV equal to constant. So therefore, dP by dV equal to minus P by V. Or dP is equal to, or P is equal to so for isothermal process, what is the bulk modulus? Equal to pressure of gas. For adiabatic process, so this will become gamma P equal to minus dP by dV. You differentiate here. So then bulk modulus for adiabatic process will be gamma P. For isobaric process dP 0, so bulk modulus will be 0. For isochoric process, this will be infinity. Bulk modulus will be infinity. For different process, the bulk modulus, elasticity will be different. Getting some basic picture. So this is the way what you should revise the polytropic process. Okay, we'll take one example. Suppose I have the processor where T square equal to constant. We have to calculate the molar capacity of this one. Using ideal gas equation, temperature I can write as PV by nR. So P cube V to power of 7 equal to constant, or P V to power of 7 by 3 will be constant. So X value will be 7 by 3. Molar capacity will be how much? Cv plus R 1 minus X. Is a monoatomic gas. We are discussing monoatomic gas. So 3R by 2. R 1 minus 7 by 3. So this will be 3R by 2. 3R minus 4. This is a molar capacity. For anything, just bring the equation of this form. Now int G is proportional to volume like this. Okay, how to find out molar capacity? Int G, what we can write? N R by gamma minus 1 T. Okay, fine. For molar capacity for this process. So this equation now will become T is equal to A gamma minus 1 nr V square. T I can write it as PV by nr. nr get cancelled. So P V to power of minus 1 A gamma minus 1. This everything is constant. Comparing with this, the value of X is minus 1. So Cv equal to R 1 minus X. Monoatomic gas. We'll choose monoatomic gas. So 3R by 2. R X value will be 1 minus of minus 1. R by 2 will be 2R. If the intensity varies with volume like this, some general thermic process, it is polytropic process. The molar capacity, you adjust everything to the formula like this, where all compare with the standard equation and get the value of X, substitute the value of X. Okay, this will be constant. This terms you need not to bother. Sir, what happened? These things. This everything will be constant. Like temperature, volume, intensity, volume, then like a pressure, temperature, anything variable. We'll take one more. Pressure, temperature varying like this. Then temperature, what we can write? T as PV by nr. So this will become P square V cube. This everything will be constant, or P equal to 3 by 2. This will be constant. P equal to Cv plus minus 2R. Cv will be for monoatomic gas 3R by 2. Now minus 6, this will be minus 6 minus 3R by 2. Okay, now molar capacity negative. Yes, it can be negative. The molar capacity can be any value between minus into plus into. What do you mean by negative sign? If it absorbs heat, temperature will decrease. If it rejects heat, temperature will increase. Molar capacity positive, if it absorbs heat, temperature will increase. If it rejects heat, temperature decreases. Molar capacity negative means if it absorbs heat, temperature will decrease. If it rejects heat, temperature will increase. General idea. Next we'll discuss the work done by the gas. This heater coil will supply the heat. Initial temperature T1, the length of this will be L1. Let area of cross section of this cylinder be A. This is a piston. What are the forces acting? P naught A, mg, and the pressure force, let it be Pa. Here we'll bring one spring also. Okay, fine. So these are the things. Now, as I supply heat, the gas will expand. You can see here that the piston started moving up. Then what all heat supplied by that equal to increase in intensity plus work done by the gas. What is the increase in intensity? Nr gamma minus 1 T2 minus T1. This is work done by the gas. What do you mean by work done by the gas? Here, if you look at here, what all the forces, the pressure force, earlier it was balancing say P1. Now it has to balance the weight of the piston. Air will exert force. And also spring got elongated, spring got compressed. And the spring force. This is springer. Then work done. So here will equate the forces. PA minus P naught A minus mg minus kx equals 0, or P equal to P naught plus mg by A plus kx by A. Work done equal to P dV. This is P naught plus mg by A plus kx by A. What is the change in volume? A into dx. 0 to x. So this will become P naught Ax mgx kx square by 2. This is actually the concept. The gas does work. What will happen to it? A part of it will be utilized to overcome the atmospheric pressure force. Remaining is utilized to increase the gravitational potential. The remaining is utilized to increase in elastic potential energy. So therefore, there should be some agent. If nobody is there, then become free expansion. This is a general idea. So what all heat supplied, a part will be converted into rise in energy, remaining will be converted into mechanical work done. Who will take that work? Increase in gravitational potential, spring compress, so elastic potential spring will increase, and work done against atmospheric pressure force. So all these things will occur here. This will be very important for JEE Advanced. JEE Main, just you should have the basic idea. There's a Carnot heat engine or the Carnot cycle. The gas is here, it is kept here, is having the volume V1. The gas is made to undergo isothermal expansion. It will attain volume V2, the temperature remaining same. Okay, fine. Next again, further it will undergo expansion, volume will become V3. Then its temperature will become TL. The gas will undergo here the adiabatic expansion, then isothermal compression. In isothermal compression, temperature at TL will be there. The volume of the gas will be from V3, it will become V4. Again the process will get repeated. So like this, it is made to undergo the cyclic process. Isothermal expansion, adiabatic expansion, isothermal compression, adiabatic expansion. So it is absorbed only here. So then, like the heat will be absorbed from the hot body. It will do cyclic process. Then it will reject heat to the cold body. Then we define efficiency as work done by net heat absorbed. Net heat absorbed will be QH. What is further W equal to? QH minus QL by QH, or efficiency equal to 1 minus QL by QH. This will be NR TL log of heat absorbed here. Heat will be rejected here, no? Will be V4 by V3. This will be NR TH log of V2 by V1. By using adiabatic expansion formula, we can eliminate V2. So this will become T1 TH V1 gamma minus 1 or V2 gamma minus 1 equal to TL V3 gamma minus 1. Similarly, TL V4 gamma minus 1 equal to TH V1 gamma minus 1. Using these formulas we can replace. I'll end up with expression TL by TH. Temperature of cold body by temperature of the hot body. There's a one formula you have to remember. And this temperature should be in Kelvin. So this will become further theta temperature of the cold body 273 by temperature of hot body by 273. You have to substitute all these things in degrees Celsius. Theta here in Kelvin. This is a basic Carnot CT engine, not there for JEE Mains, only for JEE Advanced. Just remember formula, that will be sufficient. Next we have the second law of thermodynamics. Heat cannot flow on its own from cold body to hot body. To make the heat to flow, we have to do mechanical work. Similarly, heat engine cannot convert all heat into work. And 100% of efficiency for a thermodynamic cyclic process not possible. Only statements, second law. We don't have any application problems. There's a one general idea what you have to develop here. Okay, kids, we had a brief revision of quantity of gases and thermodynamics in one shot. So if you see that almost all the different ideas, I explained it here. Now watch this video. After watching, understand all the ideas involved. Then note down all the formulas. Daily revise them. Daily read them. Memorize them. Solve PYQ. When you are solving PYQ, you will get some methodology. Okay, how to use these concepts, and that was the confidence. Until you don't read, you don't remember, you can't solve PYQ. Until you don't solve PYQ, you can't get confidence, and you can't do better in exam. So learning is very important. Learning and remembering. Read 3, 4, 5 times, 6 times. What work you are having? There's only work, no. Sir, not interested. How to study? Not interested. Also watch it, no. Sometimes boring movie also will see. Like that also not interested. Just scroll it. Just keep on scrolling. Just see it again and again, again and again, again and again. It will become memory. Though you are not interested. This is very important. The brain, what all it sees, will try to remember. Just only see it, no problem. Sir, boring, not interested. Then also you see it. As you view it again and again, again and again, no, it will become memory. Okay, kids, all the best. Prepare well, plan everything properly. So make utilize of this one shot. Next video, I'll upload the thermal properties of matter and thermal properties of matter. Okay, thank you everyone for great support. I'll end up the session.